Hi everybody. So in this video, I'm going to show you how we can use the Moivre theorem to write cos to the 5 theta in terms of each of these. And then we'll use this form to evaluate this integral. So if we begin with example A, we need to write z to the n, where z is a complex number, plus 1 over z to the n equals 2 cos n theta. So we'll begin by saying that the complex number z is equal to cos theta plus I sine theta. Then if we raise z to the power of n, this will give us, using the Moivre theorem, cos n theta plus I sine n theta. And then for 1 over z to the n, this is the same as z to the negative n. Again, using the Moivre theorem, this will be cos negative n theta plus I sine of negative n theta. And then using the properties of the cosine and the sine graph, we know this will be equal to cos of n theta minus I sine positive n theta. So if we call this one equation 1 and this one equation 2, then what we're being asked is to work out z to the n plus z to the negative n. So this is equation 1 plus equation 2. When you add these two together, we've got 2 cos n theta, and the positive I sine n theta will cancel with this negative. So we can see that z to the n plus 1 over z to the n is the same as 2 cos n theta. Okay? And then if we consider a special case when n equals 1, we'll have z to the 1 plus 1 over z. This will equal, letting this n equal 1, 2 cos theta. So it's really useful to have it when n is 1 and when n is any general number, okay? We'll use each of these as we work through question B. So for question B, we need to express cos to the 5 theta in terms of cos 5 theta, cos 3 theta, and cos theta. So the way we're going to do this is we're going to raise this term to a power of 5. So we'll have 2 cos theta to a power of 5. And then when you expand this out, we get 2 to the 5, 32, times cos to the 5 theta. And we know 2 cos theta is the same as what we have here. So this will be the same as z plus z to the negative 1 raised to the power of 5. And this will give us 32 cos to the 5 theta. So now what we need to do is expand this out using a binomial expansion. We'll make it equal to the right-hand side, then we'll divide both sides by 32. So we'll begin with z plus z to the negative 1 raised to a power of 5. So our first term will be z to the 5. Then we'll have 5 choice 1 of z to the 4 multiplied by z to the negative 1 to the power of 1. Then we'll have 5 choice 2 of z cubed and z to the negative 1 squared. Then we'll have 5 choice 3 of z squared times z to the negative 1 cubed. 5 choice 4. This will give us a z and z to the negative 1 to the 4. And then our final term will be z to the negative 1 to the power of 5. We can simplify each of these. So we'll get z to the 5 plus 5. Then we've got z to the 4 times z to the negative 1. This becomes z cubed plus 10. Z cubed times z to the negative 2 will just give us z plus another 10 to take away the negative 3, z to the negative 1 will have a power of 1, take away 4, so z to the negative 3, and then z to the negative 5. We can tidy this up further. We'll have z to the 5 plus z to the negative 5, so grouping these two terms together. Then we can factor out the 5 for these terms. This will give us z cubed plus z to the negative 3. Then we'll factor out the 10 from these terms. And we'll have z plus z to the negative 1. And now we can simplify each of these using this identity at the top, where we've got z to the 5 plus z to the negative 5 will be 2 cos of 5 theta. So we'll have 2 cos 5 theta plus the 5. Then we can substitute n equals 3 into here, and we'll get 2 cos 3 theta plus 10 lots of, this is when n is 1, so 2 cos theta. We can tidy this up again. We've got 2 cos 5 theta plus 10 cos 3 theta plus the 20 cos theta. And all of this right-hand side is equal to this, which we know is the same as this. So we'll have 32 cos to the 5 theta. We were asked to write this term in terms of what we have on the right-hand side. So all we need to do is divide both sides by 32. So cos to the 5 theta will give us 1 over 16 cos 5 theta plus 5 over 16 cos 3 theta plus 5 over 8 cos theta. And this is what we were asked to show. Okay? Then for question C, so we have our identity for cos to the 5 theta, and we can use this to evaluate this integral. But we need to let theta equal this 2 theta. So we'll say the integral has the same limits of 1/16. When we times this by 2, we'll get 10 theta plus 5/16, 6 theta plus 5/8 cos of 2 theta. And then we can evaluate this integral using the reverse chain rule. So we'll get the 1/16 divided by 10, so 1 over 160. Then we'll integrate the cos to get sine 10 theta. We'll do the same here, and we'll get 5 over 96 sine 6 theta. We'll multiply the 8 by the 2, and we get 5/16 sine 2 theta between the limits of pi over 4 and 0. And now we'll substitute in our limits. We'll have 1 over 160. 10 times pi over 4 will give us the sine of 5 pi over 2. The sine of pi over 4 will give us 3 pi over 2. And this will become pi over 2. And we can work each of these out using our sine graph. We'll have 1 at pi over 2, so this will be 1. Negative 1 at 3 pi over 2, so this will be negative 1. And 1 at 5 pi over 2. So we can work this out as 1 over 160 minus 5 over 96 plus 5 over 16. And then we need to substitute in our lower limit. And when you substitute in 0, each of these becomes 0, and the sine of 0 is 0. So all we need to do is to work out this addition. So the integral between pi over 4, 0 of cos 2 of 5, 2 theta is 4 over 15. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.